Welcome. In the first part of Chapter 1, we discussed the history of chemistry, as well as the law of conservation of mass and the law of definite proportions. During Part 2 of Chapter 2, we will continue discussing the history of chemistry. In the early 1800s, an experimentalist by the name of John Dalton came up with a theory and a law that would revolutionize our view of chemistry. His theory, atomic theory, was used to explain a variety of different laws and traits of the atoms. To start with, the law of multiple proportions was that elements may be combined in more than one set of proportion, and that each different corresponding proportion would be a different compound. For example, carbon and oxygen can be combined into 1:1 ratio to make carbon monoxide, which is a toxic chemical that's released from car exhaust, or it can be combined with carbon and oxygen in a 1:2 ratio as carbon dioxide, a compound which we exhale in the process of breathing. Dalton's atomic theory can be summarized into four major components. The first component is that all matter is composed of extremely small particles called atoms. Now, Dalton theorized that all matter is composed of extremely small and indestructible particles called atoms, and that these atoms are indivisible. But we'll see later in Chapter 3 that we can actually divide these atoms into even smaller and smaller units. The second part of his theory is that all atoms of a given element are alike, but atoms of one element are different from atoms of another. We'll also look later on that there are some small parts of this that are incorrect. Now, sections 3 and 4 of Dalton's atomic theory are that compounds formed when atoms of different elements combine are formed in fixed proportions, and that chemical reactions involve rearrangement of atoms. No atoms are created or destroyed or broken apart. Both parts 3 and 4 have remained unmodified by modern day chemistry. Let's take a look at this last bullet point. Chemical reactions involve the rearrangement of atoms. No atoms are created, destroyed, or broken apart. In the process of building compounds and molecules, we're taking atoms and we're going to bond them together through the use of chemical bonds, a topic that we'll discuss more in further chapters. And if we want to build a new molecule, we can actually break those bonds apart and rearrange the atoms, creating new bonds between the atoms to create new molecules. Here is a direct example of the law of multiple proportions. In these three compounds in Table 2.1, we have two types of atoms present, nitrogen atoms and oxygen atoms. In the first compound, we have nitrous oxide. This compound has two nitrogen atoms and one oxygen atom. In the second compound, we have nitric oxide. This is a 1:1 ratio between the nitrogen and oxygen. And then finally, in nitrogen dioxide, we have two oxygen atoms and one nitrogen atoms. All three of these compounds are unique compounds with their own masses and chemical characteristics, but they're both comprised of nitrogen and oxygen. There were a couple flaws with Dalton's theory of matter. First, Dalton assumed that atoms are indivisible, and this is not the case. And then second, that all atoms of the same element are not alike. Each element has something called an isotope. An isotope is when we have atoms of the same element that have different masses, and we'll explore this concept more in Chapter 3. One of the most notable discoveries from Dalton's experiments was the concept of the atomic mass unit. Throughout his experiments, John Dalton measured the atomic masses of various substances by combining the elements together with specific masses of one element towards another element. By using hydrogen as a standard atomic mass of 1, he was then able to calculate the atomic masses of each individual element. Today we refer to these units as the atomic mass units. Roughly 70 years later, Dmitri Mendeleev organized the elements in increasing order of atomic mass. In the process of doing this, he noticed patterns within the different properties of the elements. During this time, there were 55 known elements, and Mendeleev was able to organize them into rows and columns based on properties such as atomic mass and their electron count. One of the most remarkable parts of this periodic table was the gaps that Mendeleev left in between the elements. Over the next several decades, more and more elements would be discovered, and these gaps that were left in Mendeleev's periodic table would be filled in with the new elements. Here's an example of the original periodic table as discovered in the 1860s. Now let's revisit the origin of the chapter. Atoms, are they real? Yes, atoms are real. They're a very real concept and they're very relevant. It's possible to even observe an individual atom using computer-enhanced images. This technology is fairly new technology, but we now have the ability to predict the individual size and properties of atoms using this computer software. Molecules are groups of atoms that are chemically bonded together and represented by a chemical formula. One of the most common molecules that you are aware of in your everyday life is water. Water is composed of 2 hydrogen atoms bonded with 1 oxygen atom. In the next chapter, we'll look at a more detailed inspection of not only water, but a variety of other atoms and build molecules with these atoms.